Right now, 37 trillion cells in your body are running quantum calculations more complex than any supercomputer ever built. But what if I told you your very act of observation might help shape reality itself? This isn't science fiction. It's what happens when we follow one of the most mysterious and unsettling discoveries in all of physics to its logical conclusion. This is the story of Heisenberg's uncertainty principle, and how it might reveal that reality is not something we observe, but something we participate in. Welcome to a journey through one of the most beautiful and bewildering discoveries in all of science. I'm so glad you're here, settling in for what might just change the way you see everything around you. Whether you're curled up in a favourite chair, walking through your neighbourhood, or finding a quiet moment in your day, you've chosen to explore something extraordinary. And I have to say, there's something deeply satisfying about diving into ideas this profound together. Before we begin, if you enjoy these explorations into the deeper mysteries of science and reality, I'd be grateful if you took a moment to subscribe. It helps more curious minds find their way here. And honestly, building this community of wonder seekers means the world to me. Now let's ease into this story, because what we're about to discover together will take us from the laboratories of early 20th century Germany to the very edges of what it means for anything to be real. In 1927, in the quiet halls of the University of Göttingen, a young German physicist named Werner Heisenberg was wrestling with a problem that had been haunting the scientific community for years. The emerging field of quantum mechanics was producing results that seemed to mock common sense. Electrons weren't behaving like tiny planets orbiting atomic nuclei as everyone had hoped. Instead, they were doing something far stranger, something that challenged the very notion that objects have definite properties before we measure them. Heisenberg, barely 25 years old at the time, was part of a remarkable generation of scientists who were essentially rebuilding physics from the ground up. Imagine the intellectual courage that required. These weren't just tweaking existing theories. They were discovering that reality itself operated by rules no one had ever imagined. And Heisenberg's contribution to this revolution would prove to be perhaps the most unsettling insight of all. Working late into the night, surrounded by sheets of calculations that looked more like abstract art than physics, Heisenberg stumbled upon something that would earn him a Nobel Prize and fundamentally alter our relationship with the concept of objective reality. He discovered that nature has built-in limits to what can be known simultaneously about any quantum system. More specifically, he found that the more precisely you try to determine a particle's position, the less precisely you can know its momentum, and vice versa. But here's what makes this discovery so philosophically explosive. This isn't a limitation of our measuring instruments or a problem we might solve with better technology. According to Heisenberg's principle, this uncertainty is woven into the very fabric of reality itself. It's not that particles have definite positions and velocities that we simply can't measure accurately enough. Rather, the act of measurement itself fundamentally changes what can be known about the system being observed. Take a moment to let that sink in. We're not talking about a technical limitation or an engineering challenge. We're talking about the possibility that the universe doesn't have definite answers to certain questions. Until the moment those questions are asked, the implications are staggering, and they reach far beyond the realm of subatomic particles into the deepest philosophical questions about the nature of reality, knowledge, and our place in the cosmos. The mathematical expression of Heisenberg's principle is elegantly simple, yet its implications are anything but straightforward. The uncertainty in position multiplied by the uncertainty in momentum, must always be greater than or equal to a tiny constant, known as Planck's constant divided by 4 pi. This might sound like abstract mathematical poetry, but it describes something profound about the limits of what can be simultaneously known about the physical world. But let's step away from the equations for a moment and consider what this really means in human terms. Imagine you're trying to photograph a hummingbird in flight. To capture a sharp image of its position, you need a fast shutter speed, which freezes its motion but tells you nothing about how fast it was moving or in which direction. To study its flight pattern and velocity, you need a longer exposure, which creates a motion blur that obscures its exact position at any given moment. Now, Heisenberg's principle tells us that this trade-off isn't just a quirk of photography, it's a fundamental feature of reality at the quantum level. But here's where it gets truly strange. It's not that the hummingbird has a definite position and velocity that we're simply failing to capture simultaneously. According to quantum mechanics, the hummingbird, if it were a quantum particle, wouldn't have both definite position and definite velocity to be captured. The act of measuring one property fundamentally limits what can be known about the other. This realization sent shockwaves through the scientific community that are still reverberating today. Einstein famously struggled with these implications, spending much of his later career trying to find ways around what he saw as the incompleteness of quantum mechanics. He couldn't accept that the universe might be fundamentally probabilistic rather than deterministic, leading to his famous declaration that God does not play dice with the universe. But as we'll discover, the evidence for Heisenberg's principle has only grown stronger over the decades. Experiment after experiment has confirmed that uncertainty isn't a bug in the system of reality, it's a feature. And this feature has profound implications not just for physics, but for philosophy, consciousness, and our understanding of what it means to exist in a universe that seems to resist being fully known. To truly understand how Heisenberg's principle shatters our everyday assumptions about reality, we need to examine one of the most famous experiments in all of science, the double slit experiment. This seemingly simple setup has been called the most beautiful experiment in physics, and for good reason. It reveals the heart of quantum weirdness in a way that's both elegantly simple and profoundly disturbing to our classical intuitions. Picture this. You have a barrier with 2 parallel slits cut into it, and you're shooting particles, let's say electrons, toward this barrier. Behind the barrier, you place a detector screen that lights up wherever a particle hits it. Common sense tells us that each electron should go through one slit or the other, creating 2 bands of hits on the detector screen, one behind each slit. But that's not what happens. Instead, when no one is watching to see which slit each electron passes through, the electrons create an interference pattern on the screen, a series of bright and dark bands that can only be explained if each electron somehow goes through both slits simultaneously and interferes with itself. The electrons are behaving like waves, not particles. Now here's where Heisenberg's uncertainty principle enters the picture in the most dramatic way possible. The moment you try to observe which slit each electron passes through, by placing a detector at one of the slits, the interference pattern disappears. The electrons start behaving like ordinary particles again, each going through one slit or the other, creating exactly the 2-band pattern our common sense expects. This isn't just a quirky laboratory curiosity. This experiment demonstrates that the very act of observation changes the fundamental nature of what's being observed. The electron doesn't have a definite path until someone tries to measure which path it took. Before measurement, it exists in what physicists call a superposition of states, simultaneously taking all possible paths. The act of measurement forces it to choose a single path, collapsing the wave function and destroying the interference pattern. As you contemplate this, notice how it challenges something we rarely question: the assumption that the world has definite properties, whether we're looking at it or not. The double slit experiment suggests that reality at the quantum level is far more participatory than we ever imagined. The observer and the observed are entangled in a dance where the very act of looking changes what there is to see. The implications of Heisenberg's uncertainty principle extend far beyond the laboratory walls where it was first discovered. At its core, this principle challenges one of the fundamental assumptions of classical science and philosophy: the belief in an objective reality that exists independently of observers. For centuries, we've operated under the assumption that the universe is like a great clockwork mechanism with definite properties and predictable behaviors, whether anyone is watching or not. Heisenberg's principle suggests something radically different. It implies that the universe at its most fundamental level is not a collection of things with definite properties, but rather a web of relationships and possibilities that only become actualized through the process of measurement and observation. This doesn't necessarily mean that consciousness creates reality, a common misinterpretation we must be careful to avoid. Rather, it suggests that the boundary between the observer and the observed is far more blurred and complex than our everyday experience would suggest. Consider how this challenges our most basic intuitions about existence. When you're not in your living room, does your couch have a definite position? Classical physics would say absolutely yes. But if your couch were governed by quantum mechanics, Heisenberg's principle would suggest that in the absence of measurement, it exists in a superposition of all possible positions. Only when you walk into the room and observe it would it collapse into having a definite location. Of course, this is where the principle gets tricky when applied to large objects. The uncertainty principle technically applies to everything in the universe, from electrons to elephants, but its effects become negligible for objects much larger than atoms. Your couch doesn't noticeably exist in multiple positions simultaneously because it's constantly interacting with its environment in ways that effectively measure its position billions of times per second. The air molecules bouncing off it, the light reflecting from its surface, the gravitational interactions with nearby objects. All of these constitute continuous measurements that keep large objects locked into definite states. But the philosophical implications remain profound, even if the practical effects are limited to the quantum realm. If uncertainty is built into the foundation of reality itself, what does this say about the nature of knowledge? What does it mean for our understanding of causality? How do we reconcile this picture of reality with our everyday experience of a world that seems solid and definite? One of the most unsettling aspects of Heisenberg's uncertainty principle is how it transforms our understanding of the relationship between knowledge and reality. In classical physics, measurement was thought to be a passive process. We observe the world to discover properties that already exist. A thermometer doesn't create the temperature of the air. It simply reveals what was already there. But quantum mechanics suggests something far more radical. At the quantum level, measurement doesn't just reveal pre-existing properties, it appears to participate in creating them. This isn't because quantum systems are too small to measure without disturbing them, though that's often how the uncertainty principle is incorrectly explained in popular accounts. Rather, the evidence suggests that many properties of quantum systems simply don't have definite values before measurement. Think about this carefully. We're not saying that an electron has a definite position that we're too clumsy to measure without disturbing it. We're saying that before measurement, the electron doesn't have a definite position at all. It exists in what physicists call a superposition, a ghostly combination of all possible positions, each with its own probability. Only when a measurement forces the system to choose does it collapse into having a single, definite position. This idea is so counterintuitive that even many physicists struggle with its implications. It suggests that reality, at least at the quantum level, is not a fixed script being played out according to predetermined rules. Instead, it's more like an improvised performance where the actors don't know their lines until the moment they're called upon to speak them. The measurement problem, as it's known in quantum mechanics, remains one of the most hotly debated issues in physics and philosophy. How exactly does a measurement cause a quantum system to transition from a superposition of possibilities to a single, definite outcome? What constitutes a measurement? Does it require a conscious observer, or can any interaction with the environment trigger the collapse of the wave function? These questions touch on some of the deepest mysteries in science. They force us to confront the possibility that consciousness and physical reality are more intimately connected than we've traditionally assumed. Not in the sense that our thoughts directly create reality, a claim that lacks scientific support, but in the more subtle sense that the process of observation and knowledge gathering is woven into the very fabric of how reality unfolds. As you reflect on these ideas, you might notice how they echo certain wisdom traditions that have long suggested reality is more fluid and participatory than our everyday experience suggests. While we must be careful not to overstate the connections between quantum mechanics and consciousness, there's something profound in the recognition that the universe appears to be far more mysterious and interconnected than classical physics ever imagined. To truly appreciate how Heisenberg's uncertainty principle shatters our understanding of reality, we need to explore one of the most fundamental puzzles in quantum mechanics: wave-particle duality. This concept reveals how the uncertainty principle isn't just an abstract mathematical constraint, but a window into the truly strange nature of quantum reality. For centuries, scientists debated whether light was made of particles or waves. Newton favoured the particle theory, while others, like Thomas Young, provided compelling evidence for light's wave-like nature. The debate seemed settled in favour of waves until Einstein's work on their but quantum mechanics revealed something far stranger than photoelectric effect demonstrated that light also behaves like particles, earning him the Nobel Prize. Anyone had anticipated. Light, and indeed all matter, doesn't choose between being a particle or a wave. Rather, it exists in a kind of quantum limbo, exhibiting both properties simultaneously until the act of measurement forces it to manifest as one or the other. This isn't a limitation of our measuring instruments or a failure of our theories. It's a fundamental feature of reality itself. Consider the profound implications of this. An electron doesn't have a definite position because it exists as a spread out wave of probability. But when you try to measure its position precisely, you force it to behave like a particle with a definite location. The trade-off described by Heisenberg's uncertainty principle emerges naturally from this wave-particle duality. The more you force the electron to act like a particle with a definite position, the more wave-like it becomes in terms of its momentum, and vice versa. This creates a picture of reality that's radically different from our everyday experience. The quantum world isn't populated by tiny solid objects moving through space according to definite trajectories. Instead, it's a realm of ghostly possibilities, probability waves that ripple through abstract mathematical spaces, only crystallizing into definite properties when forced to do so by the act of measurement. But here's what makes this even more mysterious. This isn't just true for individual particles. When particles become entangled, a phenomenon Einstein called spooky action at a distance, their wave-like properties become correlated in ways that seem to transcend the normal limitations of space and time. Measuring the properties of one entangled particle instantly affects the possibilities available to its partner, even if they're separated by vast distances. This quantum entanglement, which has been verified in countless experiments, suggests that the world appears to be fundamentally non-local, meaning Heisenberg's uncertainty principle is just the tip of a much larger iceberg. The quantum that separated systems can share a kind of instantaneous connection that classical physics says should be impossible. As you contemplate these ideas, notice how they challenge our most basic assumptions about the nature of objects and the relationships between them. In our everyday world, things seem separate and independent, but quantum mechanics suggests that, at the deepest level, everything is interconnected in ways that transcend our ordinary concepts of space and time. This doesn't mean that distant objects are constantly influencing each other in ways we can directly observe that would contradict well-established physics. Rather, it suggests that the foundation of reality is far more interconnected and mysterious than our classical intuitions would ever lead us to believe. The boundaries we draw between objects, between observer and observed, between here and there, may be more fluid and contextual than we've ever imagined. One of the most philosophically challenging aspects of Heisenberg's uncertainty principle is how it transforms our understanding of the relationship between knowledge and reality. The observer effect in quantum mechanics goes far beyond the simple idea that measurement disturbs the system being measured. It suggests something much more profound, that the very act of gaining knowledge about a quantum system fundamentally changes what there is to know about it. This creates what philosophers call an epistemological crisis, a fundamental challenge to how we think about knowledge itself. In classical physics, knowledge was thought to be a kind of mapping process. Reality existed out there, with definite properties, and the goal of science was to create increasingly accurate maps of that pre-existing territory. The better our instruments and theories, the more precisely we could chart the landscape of reality. But Heisenberg's principle suggests that this mapping metaphor breaks down at the quantum level. The territory itself changes depending on what kind of map we're trying to draw. If we design an experiment to precisely map a particle's position, we create a reality where that particle has a definite position but an uncertain momentum. If we design an experiment to precisely map its momentum, we create a reality where it has definite momentum but an uncertain position. This doesn't mean that reality is arbitrary or that anything goes. The uncertainty principle provides precise mathematical limits to what can be known simultaneously. But it does suggest that reality at the quantum level is far more participatory and context-dependent than classical physics ever imagined. The observer and the observed are partners in an intricate dance where the very act of looking shapes what there is to see. Consider how this challenges our everyday assumptions about objective knowledge. When you observe the world around you, you naturally assume you're discovering properties that exist independently of your observation. The tree in your yard has a definite height, whether you measure it or not. Your coffee has a definite temperature, whether you check it or not. But if these objects were governed purely by quantum mechanics, Heisenberg's principle suggests a radically different picture. The tree wouldn't have a definite height until you measured it. Before measurement, it would exist in a superposition of all possible heights. The act of measurement wouldn't reveal a pre-existing property. It would force the tree to choose a specific height from among all the possibilities. Of course, as we've discussed, large objects like trees are constantly being measured by their environment in ways that effectively collapse their wave functions, keeping them locked into classical behavior. But the philosophical implications remain profound. If uncertainty is built into the foundation of reality, what does this mean for our concepts of truth, knowledge, and objective reality? Some interpretations of quantum mechanics suggest that these questions force us to abandon the idea of a single objective reality altogether. Instead, they propose that reality is always relative to the observer and the context of measurement. Other interpretations try to preserve objectivity by postulating that reality constantly branches into multiple parallel worlds, each corresponding to a different outcome of quantum measurements. As you sit with these ideas, notice how they might shift your relationship to certainty and knowledge in your own life. While Heisenberg's uncertainty principle applies directly only to quantum systems, its philosophical implications ripple outward into every domain of human experience. It reminds us that the very act of seeking knowledge changes both the seeker and what is sought, that observer and observed are more intimately connected than our everyday experience suggests. Take a breath here and let yourself wonder if the foundation of physical reality is built on uncertainty and participation rather than fixed properties and passive observation. What might this suggest about the nature of consciousness, creativity, and the mysterious process by which possibilities become actualized in our daily lives? We're going to explore these profound questions as we continue this journey together, diving deeper into the interpretations and implications of quantum mechanics that continue to challenge physicists and philosophers alike. But for now, let's pause and appreciate how far we've travelled from our starting point, and how much more mysterious and beautiful reality appears to be than we might have ever imagined. As we've explored how Heisenberg's uncertainty principle challenges our assumptions about measurement and knowledge, we arrive at perhaps the most mind-bending questionations of all possible states until of all. If quantum systems exist in superpose measured, what happens to all those other possibilities? Do they simply vanish into nothingness? Or might they continue to exist in some parallel realm beyond our perception? This question led physicist Hugh Everett III to propose what may be the most audacious interpretation of quantum mechanics ever conceived: the many worlds interpretation. Picture this: every time a quantum measurement occurs, every time a wave function appears to collapse into a single outcome, reality doesn't actually choose just one possibility. Instead, it branches into multiple parallel universes, each containing a different outcome. In one universe, the electron went through the left slit. In another, it went through the right. In yet another, it somehow went through both simultaneously in a way we can't directly observe. Each possibility plays out in its own separate reality, and we simply find ourselves conscious in one particular branch of this vast, ever-expanding tree of worlds. Take a moment to contemplate what this might mean for your own existence. According to the many worlds interpretation, there are countless versions of you reading these words right now. In some universes, you decided to listen to this video at a different time. In others, You chose a different video entirely. In still others, the entire history of scientific discovery unfolded differently, and quantum mechanics was never discovered at all. This isn't science fiction speculation, though it might sound like it. Some of the most respected physicists in the world take the many worlds interpretation seriously as a possible description of reality. They argue that it's the most mathematically consistent way to understand quantum mechanics without invoking the mysterious process of wave function collapse. But here's what makes this interpretation both fascinating and deeply unsettling. If it's true, then every possible version of history, every choice not made, every path not taken, exists with equal reality in some parallel branch of the multiverse. The you that decided to become a musician instead of an engineer, the you that moved to a different city, the you that said yes instead of no to that life-changing opportunity, all of these versions continue to exist and experience their own realities. As we delve deeper into the implications of quantum mechanics, we inevitably encounter one of the most contentious and fascinating questions in all of science. What role, if any, does consciousness play in the quantum realm? This question has sparked decades of debate, wild speculation, and more than a few misconceptions that we must navigate carefully. The confusion often begins with a misinterpretation of the measurement problem we discussed earlier. Some people have taken the observer effect in quantum mechanics to mean that conscious observation literally creates reality, that our thoughts and intentions can directly influence quantum events, and by extension, the physical world around us. While this idea has captured the imagination of many, it's important to understand that it lacks scientific support and represents a misunderstanding of what quantum mechanics actually tells us. When physicists talk about observation or measurement in quantum mechanics, they're not necessarily referring to conscious observation by a human mind. Rather, they're describing any interaction between a quantum system and its environment that can, in principle, provide information about the system's state. This could be a photon bouncing off an electron, a detector registering a particle's presence, or even the random thermal motions of atoms in the surrounding environment. The quantum measurement doesn't require consciousness, just interaction. A rock falling in an empty forest, to paraphrase the old philosophical puzzle, can measure quantum systems just as effectively as a human observer with sophisticated instruments. The universe is constantly measuring itself through countless interactions without any need for conscious witnesses. However, this doesn't mean that consciousness has no interesting relationship to quantum mechanics. Some interpretations suggest, though this remains highly speculative and unproven, that consciousness might somehow be connected to the process by which quantum possibilities become classical realities. But even these interpretations don't claim that consciousness creates reality through wishful thinking or positive intentions. As you reflect on these ideas, notice how they invite a more nuanced understanding of the relationship between mind and world. While your thoughts don't directly rearrange quantum particles or manifest your desires into physical reality, there's something profound in recognizing that consciousness emerges from the same quantum substrate that underlies all of physical reality. You are quite literally a pattern of consciousness arising from the dance of quantum possibilities. Perhaps no aspect of quantum mechanics challenges our classical intuitions more dramatically than quantum entanglement. Einstein famously called it spooky action at a distance, and his discomfort with the phenomenon led him to spend much of his later career searching for ways to explain it away. But decades of experiments have confirmed that entanglement is not just real, It's one of the most fundamental features of quantum reality. Here's what makes entanglement so extraordinary. When two particles become entangled, they remain connected in a way that transcends our normal understanding of space and time. Measuring the properties of one particle instantly affects the possibilities available to its entangled partner, even if they're separated by vast distances. This isn't because some signal travels between them faster than light, which would violate Einstein's relativity. Rather, it suggests that entangled particles share a kind of quantum wholeness that can't be reduced to the properties of individual parts. Imagine you have a pair of quantum coins that have become entangled in a special way. Before you flip either coin, quantum mechanics tells us that each exists in a superposition of both heads and tails. But here's the twist. The coins are entangled such that they must always land on opposite sides. If one shows heads, the other must show tails, and vice versa. Now here's where it gets truly strange. According to quantum mechanics, the coins don't decide which will show heads and which will show tails until one of them is actually flipped. The moment you flip the first coin and it lands heads, its entangled partner instantly knows that it must show tails, even if it's on the other side of the galaxy. This happens faster than light could travel between them, suggesting that the connection between entangled particles exists outside our normal concepts of space and time. This phenomenon has been verified in countless experiments, and it forms the basis for emerging technologies like quantum computing and quantum cryptography. But beyond its practical applications, entanglement reveals something profound about the nature of reality itself. It suggests that the universe is fundamentally interconnected in ways that our classical physics never imagined. Consider how this might shift your understanding of connection and relationship. While entanglement doesn't mean that distant objects are constantly influencing each other in ways we can observe directly, it does suggest that the boundaries we draw between separate things may be more fluid and contextual than we typically assume. At the deepest level of reality, everything that has ever interacted remains connected in subtle but measurable ways. As we continue our exploration of how Heisenberg's uncertainty principle resh and mysterious aspects of quantum mechanics, the relationship apace our understanding of reality, let's turn our attention to one of the most beautiful between possibility and actuality. In the classical world we inhabit daily, this distinction seems clear-cut. Things either exist or they don't. Events either happen or they don't. But quantum mechanics reveals a far more nuanced and participatory reality. In the quantum realm, possibility isn't just a measure of our ignorance about what's really happening. Rather, quantum systems appear to exist in genuine superpositions of multiple possibilities simultaneously. An electron doesn't secretly have a definite position that we simply don't know about. According to quantum mechanics, it genuinely exists in a ghostly combination of all possible positions until something forces it to actualize just one. This creates a picture of reality that's both deeply strange and oddly poetic. The universe appears to be constantly exploring all possible ways it could unfold, with countless potential futures coexisting in a kind of quantum democracy. Only through the process of interaction and measurement do some possibilities become actualized, while others fade into the realm of what might have been. Think about this in terms of your own life for a moment. Right now, as you listen to these words, you exist at a crossroads of infinite possibilities. You could pause this video and call an old friend. You could step outside and notice something beautiful in your surroundings. You could make a decision that changes the entire trajectory of your future. From a quantum perspective, all of these possibilities have a kind of ghostly reality until the moment you choose one path and all the others fade into the background. Of course, we must be careful not to overstate this connection. Your conscious choices don't directly manipulate quantum wave functions, and quantum mechanics doesn't give us magical powers to manifest our desires. But there is something profound in recognizing that you, as a conscious being, participate in the ongoing process by which possibilities become realities. As you contemplate this, you might notice how it transforms your relationship to uncertainty itself. Rather than being something to be eliminated or overcome, uncertainty begins to appear as the very foundation of creativity and possibility. It's the space within which new realities can emerge, the openness that allows the universe to surprise itself with novel forms of beauty and complexity. One of the most unsettling implications of Heisenberg's uncertainty principle, causality. In the concerns our understanding of time and classical world, cause precedes effect in a clear temporal sequence. You flip a switch, and then the light turns on. You drop a stone, and then it falls to the ground. This sequential relationship between cause and effect forms the backbone of our everyday understanding of how things work. But quantum mechanics introduces complications to this seemingly straightforward picture. In the quantum realm, the relationship between cause and effect becomes far more subtle and context-dependent. Some interpretations of quantum mechanics even suggest that future measurements can, in a sense, influence the past states of quantum systems. Consider the delayed choice quantum eraser experiment, a sophisticated version of the double slit experiment we discussed earlier. In this setup, the decision of whether to observe which slit a photon passes through can be made after the photon has already hit the detector screen. Remarkably, this future decision appears to retroactively determine whether the photon behaved like a wave or a particle during its journey. This doesn't mean that we can send messages to the past or change historical events through quantum mechanics. The effects are subtle and only visible in the statistical patterns of many quantum events. But it does suggest that our classical notions of temporal sequence and causal flow may be oversimplifications of a more complex reality. As you sit with this idea, notice how it might invite a different relationship to time itself. Perhaps the sharp distinction between past, present, and future that dominates our everyday experience is more fluid and contextual than we typically assume. Perhaps the present moment isn't just a thin slice between what was and what will be, but rather a creative space where multiple temporal possibilities come together. This doesn't mean that time is an illusion or that causality doesn't exist. Rather, it suggests that these familiar concepts may be emergent properties of a deeper, more mysterious temporal reality that quantum mechanics is just beginning to reveal. The universe may be far more creative and participatory in its relationship to time than our classical intuitions would ever suggest. As we've explored throughout this journey, one of the most persistent puzzles in quantum mechanics is the measurement problem. How and why does a quantum system transition from a superposition of possibilities to a single, definite outcome? This question sits at the heart of nearly every interpretation of quantum mechanics, and despite decades of research and debate, it remains one of the most contentious issues in all of science. The mathematical formalism of quantum mechanics is incredibly precise and successful. The Schrödinger equation describes how quantum systems evolve over time with remarkable accuracy. But this same equation suggests that quantum systems should remain in superposition indefinitely unless something external intervenes to collapse the wave function. The mathematics doesn't tell us what constitutes a measurement or why measurements have such a dramatic effect on quantum systems. This creates what philosophers call the hard problem of quantum mechanics. We can predict with extraordinary precision what will happen when we measure a quantum system, but we can't explain why measurement has such a special role in the theory. It's as if the universe has two completely different sets of rules, one for when nobody's looking and another for when measurements are being made. Some interpretations try to solve this problem by eliminating the collapse altogether. The many worlds interpretation we discussed earlier suggests that superpositions never actually collapse. They just branch into multiple parallel realities. Other interpretations propose that consciousness plays a fundamental role in the measurement process. Though this remains highly speculative and controversial, still other approaches suggest that the measurement problem dissolves when we recognize that quantum mechanics describes our knowledge about systems rather than the systems themselves. In this view, wave function collapse is simply an updating of our information rather than a physical process happening to the system being measured. As you contemplate these different possibilities, notice how they each imply a radically different understanding of the nature of reality itself. Are we living in one of countless parallel worlds? Is consciousness somehow woven into the fabric of physical reality? Or is reality itself more informational and participatory than our materialist assumptions suggest? These questions remain open, and the openness is part of what makes quantum mechanics so philosophically rich and scientifically exciting. We're living through a period of scientific history where our most fundamental assumptions about reality are still being questioned and refined. Implications for consciousness and identity. We must be careful not to overstate the connections between quantum mechanics and consciousness. There are some genuinely intriguing parallels worth exploring. Both consciousness and quantum systems seem to involve the emergence of definite experiences from a background of multiple possibilities. Both involve complex relationships between observer and observed, and both challenge our classical assumptions about the nature of reality. Consider the nature of conscious experience itself. At any given moment, you're aware of only a tiny fraction of the information available to your nervous system. Your brain is constantly selecting which sensory inputs to bring into conscious awareness while filtering out countless other signals. In a sense, consciousness involves a kind of collapse from the superposition of all possible experiences to the single stream of awareness you actually have. This parallel is metaphorical rather than literal, and we must be clear that there's no scientific consensus connecting consciousness directly to quantum mechanical processes. But the parallel does suggest that both quantum mechanics and consciousness involve the mystery of how multiple possibilities resolve into single actualities. There's also something intriguing about the relationship between identity and uncertainty. Just as quantum particles don't have definite properties independent of measurement, you might notice that your own sense of identity is more fluid and context-dependent than you sometimes assume. Who you are depends partly on the situation you're in, the relationships you're engaged with, and the aspects of yourself that you're attending to in any given moment. This doesn't mean that you don't have a stable core identity, but it does suggest that selfhood, like quantum reality, might be more participatory and relational than our everyday experience suggests. You emerge from your interactions with the world around you, just as quantum properties emerge from the process of measurement and observation. As you reflect on these ideas, you might notice how they invite a gentler relationship to the uncertainty and change that characterize human life. Rather than seeing uncertainty as a problem to be solved or a weakness to be overcome, you might begin to recognize it as the very condition that allows for growth, creativity, and the ongoing emergence of new possibilities. Before we conclude our exploration, it's worth noting that Heisenberg's uncertainty principle isn't just a philosophical curiosity. It forms the foundation for some of the most revolutionary technologies of our time. Quantum computers, for instance, harness the principle of superposition to perform certain calculations exponentially faster than classical computers. While a classical computer bit must be either 0 or 1, a quantum bit or qubit can exist in a superposition of both states simultaneously. This allows quantum computers to explore multiple computational paths at once, though the results must still be carefully extracted through measurement processes that respect the uncertainty principle. Quantum cryptography uses the fragility of quantum states to create unbreakable codes. Any attempt to intercept a quantum encrypted message necessarily disturbs the quantum states being used to encode the information, alerting the intended recipients to the presence of an eavesdropper. The uncertainty principle becomes a feature rather than a limitation, providing security through the very impossibility of perfect measurement. These technologies remind us that the strangeness of quantum mechanics isn't just an abstract philosophical puzzle. It's a description of how reality actually works at its most fundamental level, and learning to work with this strangeness rather than against it opens up possibilities that would be impossible in a classical universe. As you consider these applications, notice how they embody a different relationship to uncertainty and limitation. Rather than seeing the constraints imposed by quantum mechanics as obstacles to overcome, these technologies find ways to transform those constraints into new capabilities. They work with the grain of quantum reality rather than against it. This suggests a broader principle that might apply to many areas of life. Sometimes the most creative solutions emerge not from fighting against limitations, but from finding ways to dance with them, to discover the hidden opportunities within apparent constraints. As we near implications of Heisenberg's uncertainty, the end of our journey through the principle, let's pause to appreciate how far we've traveled from our starting point. We began with the simple observation that there are fundamental limits to what can be simultaneously known about quantum systems. But this seemingly technical constraint has opened up vistas of philosophical possibility that continue to reshape our understanding of reality itself. We've seen how the uncertainty principle challenges our assumptions about objective reality, suggesting that the boundary between observer and observed is far more complex than classical physics imagined. We've explored how it transforms our understanding of possibility and actuality, revealing a universe that exists in a constant state of creative potential until interactions force possibilities into definite outcomes. We have contemplated how quantum entanglement reveals hidden connections that transcend our normal concepts of space and time, and how the measurement problem continues to puzzle physicists and philosophers alike. We've considered the implications for consciousness and identity, while being careful not to overstate the connections or make unsupported claims about the power of mind over matter. Throughout this exploration, one theme has emerged repeatedly. The universe appears to be far more participatory, relational, and mysterious than our everyday experience suggests. This doesn't mean that anything goes or that reality is arbitrary. The mathematical precision of quantum mechanics demonstrates that even uncertainty follows precise laws. But it does suggest that we live in a universe that is constantly creating itself through the interactions between its parts. As you sit with these ideas, you might notice how they invite a different quality of attention to your own experience. Perhaps the uncertainty and change that characterize daily life begin to appear less as problems to be solved and more as expressions of the creative principle that animates reality itself. Perhaps the boundaries between self and world, between knowledge and mystery, begin to seem more fluid and dynamic than you previously imagined. This shift in perspective doesn't require you to abandon critical thinking or embrace unsupported claims about quantum consciousness or reality manifestation. Rather, it invites a more nuanced appreciation for the genuine mysteries that quantum mechanics has revealed, and a greater willingness to sit with questions that may not have simple answers. Take a breath here and allow yourself to wonder if uncertainty is woven into the very fabric of reality. What might this mean for how you approach the unknowns in your own life? How might it change your relationship to the questions up when you learn to dance that matter most to you? What new possibilities might open with uncertainty rather than fight against it? These questions don't have predetermined answers, and that's precisely the point. Like the quantum systems we've been exploring, they exist in a superposition of possibilities, waiting for your unique perspective and experience to help collapse them into new insights and understanding. As we prepare to conclude this exploration together, remember that the journey we've taken isn't just an intellectual exercise. The principles we've discovered operating at the quantum level ripple outward into every domain of experience, inviting a more participatory, creative, and mysteriously connected way of being in the world. The uncertainty principle doesn't just describe the behavior of electrons and photons. In its deepest implications, it describes something essential about the nature of existence itself. That reality is not a fixed script being played out according to predetermined rules, but an ongoing improvisation in which observer and observed, knower and known, are partners in the dance of becoming. If you found this exploration of quantum reality as fascinating as I have, you might enjoy diving even deeper into these mysteries. Next, I'd love to take you on a journey through the observer effect, how consciousness shapes reality at the quantum level, where we'll explore the delicate relationship between awareness and the physical world with the nuance and scientific rigor these profound questions deserve. As we've journeyed through the implications of Heisenberg's uncertainty principle, we've touched on perhaps the most enigmatic aspect of quantum reality, its relationship with time itself. But there's something even more profound lurking beneath the surface, something that challenges not just our understanding of measurement and observation, but our most basic assumptions about the nature of temporal flow. Consider this curious fact that emerges from the mathematics of quantum mechanics. Time, unlike position or momentum, doesn't have a corresponding operator in the standard formulation of quantum theory. While we can speak precisely about the uncertainty in a particle's location or velocity, time occupies a peculiar status in quantum mechanics. It's treated as a parameter rather than an observable quantity, flowing Schrödinger equation. Uniformly in the background, while quantum systems evolve according to the... This might seem like a technical detail, but it reveals something startling about the nature of reality. If quantum mechanics is our most fundamental description of how the universe works, why does time play such an asymmetric role compared to space? And what does this asymmetry tell us about the deeper structure of existence? The answer leads us into territory that's both mathematically precise and philosophically dizzying. Some interpretations suggest that time itself might emerge from more fundamental quantum processes, rather than being the stage upon which quantum events unfold. Picture this: what we experience as the smooth flow of time might actually be the result of countless quantum interactions, each one contributing to the appearance of temporal progression. Take a moment to sit with this possibility. The experience you're having right now of one moment flowing into the next might not be a fundamental feature of reality, but rather an emergent property arising from the complex dance of quantum possibilities becoming actualized through measurement and interaction. And as you reflect on your own experience of time, you'll notice something that seems almost too obvious to mention. Time has a direction. You remember the past, but not the future. Eggs can be scrambled, but not unscrambled. Coffee grows cold, but doesn't spontaneously reheat. This directional quality of time, what physicists call the arrow of time, presents a fascinating puzzle when viewed through the lens of quantum mechanics. The fundamental equations of quantum mechanics, like most of physics, are time reversible. If you could run a quantum system backward, it would retrace its steps perfectly, returning to its initial state. Yet our everyday experience is filled with irreversible processes. How does irreversibility emerge from reversible quantum laws? The answer involves one of the most beautiful connections between the microscopic quantum world and our macroscopic experience. When quantum systems interact with their environment, a process called decoherence occurs. The delicate quantum superpositions that allow particles to exist in multiple states simultaneously become entangled with countless environmental factors, effectively erasing the quantum coherence that would allow the process to be reversed. Think of it this way: when you observe a quantum measurement, you're not just interacting with the quantum system itself, you're becoming entangled with it, and through you, the entire environment becomes entangled with the measurement outcome. This web of entanglement spreads outward like ripples in a pond, making it practically impossible to reverse the process and return to the original superposition. This suggests something profound about the relationship between quantum mechanics and our experience of temporal flow. The arrow of time might not be imposed on the universe from outside, but rather might emerge from the quantum process of entanglement itself. Each measurement, each interaction, each moment of decoherence contributes to the irreversible flow that we experience as time moving forward. As you contemplate this, notice how it transforms the relationship between the microscopic and macroscopic worlds. You're not separate from the quantum realm, observing it from some classical vantage point. Rather, you're deeply embedded in the web of quantum interactions that gives rise to the very experience of temporal flow. Your consciousness emerges from and participates in the same quantum processes that create the arrow of time itself. To truly understand how Heisenberg's uncertainty principle reshapes our view of reality, we need to venture into the deepest level of physical description we currently possess: quantum field theory. This framework, which underlies our most successful theories of particle physics, reveals that what we think of as empty space is actually seething with quantum activity. According to quantum field theory, every point in space is occupied by quantum fields, invisible substrates that can give rise to particles when sufficiently excited. But here's where Heisenberg's uncertainty principle enters in a truly remarkable way. These fields can never be perfectly still. Even in the vacuum of empty space, quantum fields are constantly fluctuating, creating virtual particles that pop into existence and annihilate each other in time frames so brief they can never be directly observed. These vacuum fluctuations aren't mathematical artifacts or approximations. They have measurable effects on the physical world. The Casimir effect, for instance, demonstrates that the quantum vacuum exerts real forces on physical objects. When two metal plates are placed very close together, they exclude certain wavelengths of vacuum fluctuations from the space between them, creating an imbalance that pushes the plates together with a force that can be measured in laboratory experiments. Picture yourself sitting quietly and imagine that the seemingly empty space around you is actually alive with this invisible quantum activity. Virtual photons are constantly appearing and disappearing. Virtual electron-positron pairs are briefly materializing before annihilating each other. The very vacuum is a dynamic, fluctuating medium that underlies all of physical reality. This quantum view of empty space transforms our understanding of what it means for something to exist. In the classical picture, particles were like little billiard balls moving through empty space. But quantum field theory suggests that particles are more like persistent excitations in an underlying sea of quantum activity. The boundary between something and nothing, between existence and non-existence, becomes far more subtle and dynamic than our everyday experience would suggest. As you sit with this image, you might notice how it echoes certain contemplative insights about the nature of experience itself. Just as quantum fields are never perfectly still, your own awareness is never completely empty or static. Thoughts, sensations, and perceptions are constantly arising and passing away, like quantum fluctuations in the field of consciousness. This parallel is metaphorical rather than literal, but it suggests a deep resonance between the structure of physical reality and the structure of conscious experience. One of the most startling developments in theoretical physics over the past few decades has been the growing recognition that information might be more fundamental than matter and energy. This insight, which emerges from the study of black holes and quantum gravity, suggests that the three-dimensional reality we experience might actually be encoded on a two-dimensional surface, like a hologram. The holographic principle proposes that all the information contained in a volume of space can be stored on its boundary. This isn't just a curiosity about data storage, it's a fundamental statement about the nature of reality itself. It suggests that what we experience as three-dimensional space might actually be a kind of projection from information encoded on a distant boundary. While this remains highly speculative and is far from proven, the holographic principle has profound implications for how we understand the relationship between information, consciousness, and physical reality. If reality is fundamentally informational rather than material, then consciousness, which is clearly an information processing phenomenon, might have a more central role in the structure of the universe than our materialist assumptions would suggest. This doesn't mean that consciousness creates reality in some magical sense, but it does raise fascinating questions about the relationship between subjective experience and objective physical processes. Some interpretations suggest that consciousness might be the universe's way of experiencing itself, the means by which the information encoded in quantum fields becomes actualized into conscious experience. Take a breath here and consider what this might mean for your own sense of identity and place in the cosmos. If you're fundamentally a pattern of information arising from quantum processes, then the boundary between you and the rest of the universe becomes far more fluid than it initially appears. You're not separate from the cosmic dance of quantum fields and information processing. You're an expression of it, a way that the universe becomes conscious of itself. As we explore these deepest implications of quantum mechanics, we encounter one of the most important concepts for understanding how the microscopic quantum world gives rise to our macroscopic experience: emergence. Emergence refers to the way that complex systems, can exhibit properties and behaviors that are not present in their individual components. Consider how the wetness of water emerges from the interactions of individual H2O molecules, none of which are themselves wet. Or how the property of temperature emerges from the statistical behavior of countless molecular motions, even though individual molecules don't have temperature. In each case, new properties emerge at higher levels of organization that weren't present at the lower levels. Consciousness itself appears to be an emergent property arising from the complex interactions of neurons, none of which are individually conscious. But here's what makes this particularly intriguing from a quantum perspective. The emergence of consciousness from neural activity might itself depend on quantum processes occurring within the brain's cellular structures. While this remains highly speculative and controversial, some researchers have proposed that quantum coherence in microtubules within neurons might play a role in generating conscious experience. Others suggest that quantum entanglement between neurons might contribute to the binding of conscious experience into a unified whole. These ideas remain unproven and are actively debated, but they illustrate how quantum mechanics might connect to consciousness in ways that are more subtle than direct mind-over-matter causation. As you contemplate these possibilities, notice how they invite a more nuanced understanding of the relationship between levels of reality. Your conscious experience emerges from neural activity, which emerges from cellular processes, which emerge from molecular interactions, which emerge from quantum field fluctuations. You exist simultaneously at all these levels, from the quantum to the conscious, each level exhibiting properties that weren't present at the levels below. This multi-level view of reality suggests that reductionism, while powerful, might not tell the complete story. Understanding the parts doesn't always give you complete understanding of the whole. New properties, new forms of organization, new types of relationships emerge at each level of complexity. The quantum world gives rise to the classical world, which gives rise to the biological world, which gives rise to the conscious world, each level adding something genuinely new to the story of existence. As we near the conclusion of our exploration, let's return to one of the most profound implications of everything we've discovered. The suggestion that we live in what some physicists call a participatory universe. This doesn't mean that our thoughts directly create reality, or that we can manifest our desires through quantum mechanics. Rather, it means that the traditional distinction between observer and observed, between subjective experience and objective reality, is more complex and interconnected than classical physics suggested. The participatory nature of quantum reality operates at multiple levels. At the most basic level, the act of measurement participates in determining which quantum possibilities become actualized. The observer doesn't create these possibilities, but the process of observation plays a role in which possibilities become real and which fade into the background of might-have-beens. At a deeper level, consciousness itself might be a participatory phenomenon. Rather than being something that happens inside your head while you observe an external world, consciousness might be the universe's way of experiencing itself from countless different perspectives. Your individual awareness might be one local manifestation of a more fundamental cosmic process of self-recognition and experience. This participatory view doesn't diminish the importance of scientific objectivity or suggest that reality is arbitrary. The quantum world follows precise mathematical laws, and those laws constrain what kinds of participation are possible. But it does suggest that the universe is more like an ongoing conversation than a predetermined script, with consciousness playing a genuine role in how that conversation unfolds. As you sit with this possibility, notice how it might transform your relationship to uncertainty and mystery in your own life. Rather than seeing unknowns as problems to be solved or gaps in knowledge to be filled, you might begin to appreciate them as spaces of creative potential, opportunities for genuine novelty to emerge. The participatory universe doesn't require you to believe in magical thinking or abandon critical reasoning. Instead, it invites a more collaborative relationship with reality, a recognition that your awareness and choices participate in the ongoing process by which possibilities become actualities. Throughout this journey, we've seen how Heisenberg's uncertainty principle reveals that the universe is far more mysterious, creative, and participatory than our classical intuition suggested. But perhaps the most practical wisdom that emerges from quantum mechanics has to do with how we relate to uncertainty itself. In uncertainty as a problem to be solved, our everyday lives, we often treat a source of anxiety to be eliminate knowledge to be corrected. But quantum, or a sign of inadequate mechanics, suggests that uncertainty is woven into the very fabric of reality. It's not a bug in the system, it's a feature. It's the space within which creativity, novelty, and genuine choice become possible. This doesn't mean that everything is uncertain or that knowledge is impossible. Quantum mechanics is one of the most precisely tested theories in all of science. But it does mean that perfect certainty about all aspects of reality simultaneously is not just practically difficult, it's theoretically impossible. As you reflect on this, consider how it might shift your relationship to the uncertainties in your own life. Rather than seeing them as obstacles to overcome or problems to solve, you might begin to appreciate them as expressions of the same creative principle that allows quantum systems to exist in superposition, that enables genuine novelty to emerge from the interaction of possibilities. The uncertainty principle teaches us that some questions don't have predetermined answers waiting to be discovered. Instead, the answers emerge through the process of inquiry itself, shaped by how we choose to engage with the mystery. This is true not just for quantum measurements, but for the deepest questions about meaning, purpose, and identity that characterize human existence. As we conclude our exploration of how Heisenberg's uncertainty principle shatters our understanding of reality, let's take a moment to appreciate the profound shift in worldview we've experienced together. We began with the simple observation that certain properties of quantum systems cannot be simultaneously determined with perfect precision. But this seemingly technical constraint has opened up an entirely new way of understanding the nature of existence itself. We've discovered that reality, at its deepest level, is not composed of solid, separate objects with definite properties. Instead, it appears to be a web of relationships and possibilities, constantly creating itself through the process of interaction and measurement. We've seen how observation and reality are more intimately connected than classical physics ever imagined, though not in the magical way that popular misconceptions suggest. We've explored how quantum entanglement reveals hidden connections that transcend our normal concepts of space and time, and how the arrow of time itself might emerge from quantum processes. We've contemplated the possibility that consciousness and physical reality arise from the same fundamental quantum substrate, though always with appropriate caution about what science can and cannot currently support. Throughout this journey, one insight has emerged repeatedly. The universe appears to be far more creative, mysterious, and participatory than our everyday experience suggests. This doesn't require abandoning scientific rigor or embracing unsupported claims. Rather, it invites a deeper appreciation for the genuine mysteries that quantum mechanics has revealed and a more nuanced understanding of our place within them. As you return to your daily life, carrying these insights with you, you might notice subtle shifts in how you experience uncertainty, relationship, and the nature of existence itself. The solid world of separate objects that classical physics described doesn't disappear, but it begins to reveal itself as a higher level pattern emerging from something far more fluid and interconnected. Take a final breath with me here and allow yourself to rest in the mystery we've explored together. You don't need to understand every implication or resolve every paradox. The quantum world, like the deepest aspects of existence itself, remains beautifully mysterious despite our best efforts to comprehend it fully. This mystery isn't a failure of human knowledge. It's an invitation to a more humble, more wondering, more participatory relationship with reality. As you move through your days, you might occasionally remember that the solid ground beneath your feet, the air you breathe, the very atoms of your body are all engaged in the same quantum dance we've been exploring, constantly creating themselves anew through interactions too subtle and swift to be directly observed. The uncertainty principle doesn't just describe the behavior of electrons and photons. In its deepest implications, it reveals something essential about the nature of existence. That reality is not a fixed stage upon which predetermined events unfold, but an ongoing creative process in which mystery and manifestation dance together in ways that remain wonderfully, beautifully uncertain. And perhaps that's exactly as it should be. In a universe where everything was predetermined and perfectly knowable, there would be no room for genuine surprise, no space for authentic choice, no possibility for the kind of creative emergence that gave rise to galaxies, to life, to consciousness, and to the very capacity for wonder that has brought us together on this journey. As you sit listening to these words right now, approximately 37 trillion cells in your body are performing quantum calculations more complex than any supercomputer ever built. Each cell contains thousands of molecular machines that rely on quantum tunneling to function, while the very thoughts emerging in your mind may depend on quantum processes occurring in structures smaller than viruses. But here's what makes this truly extraordinary. The same mathematical principles that describe these quantum events in your body also suggest that the act of conscious observation might play a fundamental role in how physical reality unfolds. This isn't mysticism. It's what happens when we follow the implications of our most rigorously tested scientific theories to their logical conclusions. Welcome to an exploration that sits at the fascinating intersection of quantum physics and consciousness studies. I'm delighted you're here, whether you're settling into a comfortable chair for a quiet evening, taking a contemplative walk, or finding a moment of stillness in your day. What we're about to discover together challenges some of our deepest assumptions about the relationship between mind and matter, between inner experience and outer reality. Before we begin this journey, if you find these kinds of explorations meaningful, where rigorous science meets philosophical wonder, I'd be grateful if you took a moment to subscribe. It helps build this community of thoughtful minds, and honestly, knowing you're part of this conversation makes creating these explorations deeply fulfilling. Now let's ease into a story that begins in the laboratories of quantum physics, but leads us into territory that's both scientifically grounded and personally transformative. In 1909, nearly 2 decades before Heisenberg would formulate his uncertainty principle, a series of experiments were beginning to reveal something that would fundamentally challenge our understanding of the relationship between observation and reality. These weren't grand theoretical proclamations or philosophical speculations. They were careful, methodical investigations that would eventually force physicists to confront an uncomfortable possibility: that consciousness might not be separate from the physical world it observes. The double slit experiment, which we touched on earlier, was revealing something that went beyond mere particle behavior. When researchers tried to determine which slit each photon passed through by placing detectors at the slits, the wave interference pattern disappeared. The photons began behaving like discrete particles rather than waves. But here's what made this truly puzzling. The change in behavior occurred regardless of whether anyone actually looked at the detector readings. This suggested something profound about the nature of measurement itself. It wasn't human consciousness that was changing the photon's behavior. It was the mere possibility of gaining information about the photon's path. The universe, it seemed, responded to the potential for knowledge, not just to conscious observation. This distinction is crucial, and it opens up fascinating questions about the relationship between information, measurement, and physical reality. As you contemplate this, take a moment to notice your own process of attention. Right now, as you focus on these words, countless other sensory experiences are available to your awareness. Sounds in your environment, sensations in your body, peripheral visual information. Your consciousness is constantly selecting which aspects of available information to bring into focus, while others remain in the background. While this parallel to quantum measurement is metaphorical rather than literal, it hints at deep connections between the nature of attention and the structure of reality itself. But the story gets even more intriguing when we consider what physicists call delayed choice experiments. In these setups, the decision of whether to measure which path a photon takes can be made after the photon has already passed through the slits, but before it hits the final detector screen. Remarkably, this future decision appears to retroactively determine whether the photon behaved as a wave or particle during its earlier journey through the apparatus. These experiments don't violate causality in the classical sense. No information travels backward in time, but they do suggest that the relationship between measurement and reality is far more subtle and non-local than our everyday experience would lead us to expect. The implications ripple outward from the quantum realm into fundamental questions about the nature of time, causality, and the role of observation in physical reality. To understand how quantum physics might relate to consciousness, we need to explore one of the most beautiful and mysterious aspects of quantum mechanics: the relationships between potential and actual states of being. In the quantum world, particles don't simply exist in definite states until measured. Rather, they exist in what physicists call superpositions, ghostly combinations of all possible states, each with its own probability of being actualized through measurement. This creates a picture of reality that's both mathematically precise and philosophically profound. Before measurement, a quantum system exists in a realm of pure possibility, where multiple potential realities coexist in a delicate dance. Only through interaction with a measuring device does one possibility become actualized, while others fade into the background of what might have been. Now, some interpretations of quantum mechanics suggest, and I emphasize that this remains highly speculative and without scientific consensus, that consciousness might play a role in this process of actualization. Not in the sense that our thoughts directly create reality, which lacks scientific support, but in the more subtle sense that conscious observation might participate in the transition from quantum possibility to classical actuality. Consider the famous thought experiment known as Schrödinger's cat, proposed by physicist Erwin Schrödinger in 1935. A cat is placed in a sealed box with a quantum device that has a 50% chance of triggering a mechanism that would be fatal to the cat. According to the mathematics of quantum mechanics, before anyone opens the box to observe the result, the cat exists in a superposition of being both alive and dead simultaneously. This paradox was intended to highlight the absurdity of applying quantum principles to macroscopic objects, but it also raises fascinating questions about the role of observation in determining reality. Some interpretations suggest that the act of opening the box and observing the cat state is what collapses the superposition and actualizes one outcome or the other. Take a breath here and allow yourself to wonder. If quantum systems exist in superpositions of possibilities until observed, what might this suggest about the unobserved aspects of your own experience? When you're not paying attention to your breathing, does it exist in some kind of experiential superposition? When you're not focusing on your emotional state, might it hover between multiple possibilities until the moment you direct your attention toward it? These parallels are metaphorical rather than literal. Your breathing doesn't literally exist in quantum superposition, but they point towards something intriguing about the participatory nature of both quantum measurement and conscious attention. In both cases, the act of observation seems to play a role in determining which of many possibilities becomes actualized in experience. While we must be extremely careful not to overstate the connections between quantum mechanics and consciousness, there are some genuinely fascinating parallels worth exploring. Both quantum systems and conscious experience seem to involve the emergence of definite states from backgrounds of multiple possibilities. Both involve complex relationships between observer and observed, and both challenge our classical assumptions about the independence of objective reality from the processes that measure or experience it. Recent research in neuroscience has revealed that consciousness involves a constant process of selection and integration. Your brain is continuously processing millions of bits of sensory information, but only a tiny fraction of this information reaches conscious awareness. The process by which some information becomes conscious, while other information remains unconscious, bears striking resemblance to the quantum measurement problem. How do multiple possibilities collapse into a single, actualized outcome? Some researchers have proposed, though this remains highly speculative and controversial, that quantum processes in the brain might play a role in consciousness. The physicist Roger Penrose and anesthesiologist Stuart Hameroff have suggested that quantum coherence in microtubules within neurons might be involved in generating conscious experience. Other researchers have proposed that quantum entanglement between neurons might contribute to the binding of conscious experience into a unified whole. These ideas remain unproven and are actively debated within the scientific community. Many neuroscientists argue that the brain is too warm and noisy for quantum coherence to persist long enough to influence neural processing. Others point out that there's no clear mechanism by which quantum effects in microtubules could give rise to the rich phenomenology of conscious experience. However, recent research has shown that quantum effects can persist in biological systems longer than previously thought. Photosynthesis, for instance, appears to rely on quantum coherence to achieve its remarkable efficiency in capturing and transferring energy. Some birds may use quantum entanglement in their navigational systems. These discoveries suggest that biology might be more quantum than we previously imagined, though this doesn't necessarily support specific theories about quantum consciousness. As you reflect on these possibilities, notice that the question isn't whether consciousness directly manipulates quantum systems. There's no scientific evidence for such direct influence. Rather, the intriguing possibility is that consciousness and quantum systems might both emerge from similar underlying principles involving the selection of definite outcomes from fields of possibility. One of the most fascinating aspects of consciousness research is how it parallels some of the challenges faced in quantum mechanics. Just as quantum systems seem to change when measured, conscious experiences often shift when we turn our attention toward them. The very act of introspection can alter what we find when we look inward. Consider your emotional state right now. Before I asked you to consider it, you might not have been explicitly aware of what you are feeling. But the moment you direct your attention toward your emotional state, something definite emerges from what was previously in the background of awareness. This isn't because the emotion didn't exist before you noticed it, but rather because the act of observation plays a role in how emotional experience becomes conscious and definite. This observer effect in consciousness isn't just a curiosity, it has profound implications for how we understand the nature of self-knowledge and inner experience. Meditation practices, for instance, often involve carefully observing the contents of consciousness without trying to change them. But practitioners quickly discover that the very act of observation inevitably influences what's being observed. Thoughts that seem solid and persistent when unexamined often dissolve when observed directly. Emotions that felt overwhelming when left unattended sometimes transform when met with gentle awareness. Physical sensations that were barely noticeable suddenly become vivid when attention is directed toward them. This suggests that consciousness isn't just a passive mirror reflecting pre-existing mental contents, but an active participant in determining which aspects of inner experience become actualized in awareness. Some interpretations of contemplative traditions suggest that this observer effect in consciousness points towards something fundamental about the nature of experience itself. When we observe the contents of consciousness carefully, we often discover that the observer and the observed are not as separate as they initially appear. The boundary between the one who observes and what is observed begins to seem more fluid and contextual than our everyday assumptions suggest. This doesn't mean that the self is an illusion or that individual consciousness doesn't exist. Rather, it suggests that the relationship between awareness and its contents might be more participatory and less clearly bounded than we typically assume. Just as quantum systems and their measurements are entangled in ways that challenge classical notions of independence, consciousness and its contents might be more intimately interconnected than our ordinary experience suggests. Take a moment to explore this for yourself. Notice how your breath feels right now. As you direct your attention toward the sensations of breathing, observe how the quality of the experience changes. The breath that was previously automatic and unconscious becomes vivid and present. Your awareness doesn't create the breath, but it participates in how the experience of breathing unfolds in consciousness. One of the most puzzling aspects of quantum mechanics is the phenomenon of entanglement, the way that quantum systems can remain instantaneously connected across vast distances. When two particles become entangled, measuring the properties of one immediately affects the possibilities available to its partner, regardless of the spatial separation between them. Einstein famously called this spooky action at a distance, but decades of experiments have confirmed that entanglement is a fundamental feature of quantum reality. This non-local connectivity in the quantum realm raises fascinating questions about the nature of consciousness and its relationship to physical reality. While we must be clear that there's no scientific evidence for direct quantum entanglement between human minds, there are some intriguing parallels worth exploring metaphorically. Consider how your consciousness seems to be intimately connected to experiences that are technically outside your physical boundaries. When you feel empathy for another person, you're somehow participating in their emotional state. When you read these words, you're connecting with ideas and meanings that originated in another mind. When you remember a conversation with a friend, you're accessing not just your own memories, but something that emerged from the interaction between two conscious beings. These connections don't violate the laws of physics. They're mediated by ordinary physical processes like language, facial expressions, and shared cultural meanings. But they do suggest that consciousness has a naturally interconnected quality that resembles the non-local connectivity observed in quantum systems. The boundaries we draw around individual minds might be more conventional than fundamental. Some researchers have investigated whether consciousness might exhibit non-local properties similar to quantum entanglement. Studies of telepathy, remote viewing, and other purported psychic phenomena have produced mixed results, with most mainstream scientists remaining skeptical due to difficulties in replication and controlling for conventional explanations. However, a small number of researchers continue to investigate these possibilities using rigorous experimental protocols. More intriguingly, some studies have suggested that meditation and other contemplative practices might enhance the sense of connection between practitioners. While these effects are likely mediated by conventional psychological and social mechanisms rather than quantum entanglement, they point toward the naturally interconnected quality of conscious experience. As you sit with these ideas, you might notice your own sense of connection to the broader field of consciousness that these words are emerging from. You're not just passively receiving information, but actively participating in a kind of meeting of minds that transcends the physical boundaries of individual brains. This participation doesn't require quantum entanglement to be meaningful. It's a fundamental feature of how conscious beings share ideas and experiences. One of the most elegant ways to explore the parallels between quantum mechanics and consciousness is through the metaphor of thought as quantum superposition. While this is purely metaphorical rather than literal, it offers fascinating insights into how conscious experience might emerge from unconscious possibilities. Before you have a specific thought, countless potential thoughts exist in the background of your mind. Most of these possibilities never reach conscious awareness. They remain in a kind of mental superposition, hovering between existence and non-existence. Only occasionally does one thought emerge into the clear light of consciousness, while countless others fade back into the unconscious background. This process bears a striking resemblance to quantum wave function collapse. Just as quantum systems exist in superpositions of multiple states until measurement forces them to actualize one possibility, thoughts might exist in superpositions of multiple meanings until attention crystallizes one specific thought into conscious awareness. Consider creativity and insight as examples of this process. When you're working on a creative problem, you often sense that a solution is hovering just beyond conscious reach. Multiple potential solutions exist in a kind of creative superposition, each with its own probability of emerging into awareness. Then suddenly, one possibility crystallizes into a clear insight, while the others fade into the background. The mathematician Jacques Hadamard studied this process extensively, interviewing prominent scientists and mathematicians about how insights emerge in their work. Many reported that solutions to complex problems often appeared suddenly in consciousness, fully formed, after periods of unconscious incubation. The process seemed to involve the unconscious exploration of many possibilities before one solution emerged into conscious awareness. This parallel between quantum measurement and conscious insight remains metaphorical. There's no evidence that thoughts literally exist in quantum superposition. But the metaphor illuminates something important about how conscious experience emerges from unconscious processes. Both quantum systems and minds seem to involve the actualization of definite outcomes from fields of possibility. Take a moment to observe this process in your own experience. Allow your mind to rest in a state of open awareness without trying to think about anything specific. Notice how thoughts occasionally emerge from this open space, crystallizing into definite meanings before dissolving back into the background. This isn't quantum mechanics in the literal sense, but it reveals something profound about how consciousness selects specific contents from the vast field of possible experiences. As we've explored these parallels between quantum mechanics and consciousness, a deeper pattern has begun to emerge. Both quantum systems and conscious experience seem to involve what physicist John Wheeler called participatory reality, a universe where observers and observed are more intimately connected than classical physics suggested. In the quantum realm, the act of measurement participates in determining which possibilities become actualized. The observer doesn't create quantum systems, but the process of observation plays a genuine role in how quantum possibilities unfold into definite outcomes. Similarly, consciousness doesn't create the contents of experience, but conscious attention participates in determining which aspects of potential experience become actualized in awareness. This participatory quality extends beyond individual consciousness to include the social and cultural dimensions of human experience. The meanings we discover in life aren't simply found lying around in objective reality, waiting to be discovered. Rather, they emerge from the ongoing interaction between consciousness and the world, shaped by our questions, our attention, and our interpretive frameworks. Consider how the act of scientific observation itself participates in revealing the structure of reality. Scientists don't just passively discover pre-existing facts about the world. Rather, they participate in an ongoing dialogue with nature, asking questions and receiving answers that are shaped by the questions themselves. The reality that science reveals is neither purely objective nor purely subjective, but emerges from the interaction between conscious inquiry and natural phenomena. This participatory understanding doesn't undermine scientific objectivity, it enriches it. When we recognize that observation always involves some degree of participation, we become more conscious of our role in the process of discovery. We can design experiments more carefully, account for observer effects more thoroughly, and remain humble about the limitations of any particular perspective on reality. As you reflect on your own experience, you might notice how participatory your relationship with reality actually is. You're not just passively observing the world around you, but actively participating in how your experience unfolds. Your questions shape what you discover. Your attention influences what becomes vivid in awareness. Your interpretive frameworks affect what meanings emerge from the flow of experience. This doesn't mean that reality is arbitrary or that anything goes. Just as quantum mechanics involves precise mathematical constraints on what kinds of measurements are possible, Consciousness operates within natural limits on what kinds of experiences can emerge. But within these constraints, there's genuine creativity and participation in how reality unfolds. To explore the deepest parallels between quantum mechanics and consciousness, we need to venture into the concept of fields, one of the most fundamental ideas in modern physics. Rather than thinking of particles as little balls moving through empty space, quantum field theory describes particles as excitations in underlying fields that permeate all of space. The electromagnetic field, for instance, exists everywhere in space, and what we call photons are simply localized excitations in this field. Similarly, the electron field exists throughout space, and what we call electrons are excitations in this field. This field-based view of reality suggests that what we think of as separate particles are actually local manifestations of more fundamental interconnected fields. Some interpretations of consciousness suggest a similar field-like quality to awareness itself. Rather than thinking of consciousness as something that exists inside individual brains, these approaches propose that consciousness might be more like a field, a fundamental feature of reality that can become localized and individuated through complex neural processes, but isn't ultimately confined to individual organisms. This field theory of consciousness remains highly speculative and lacks scientific consensus. However, it offers an intriguing framework for understanding some of the puzzling features of conscious experience. If consciousness has field-like properties, it might help explain the sense of unity and interconnection that many people report in deep meditative states, the apparent non-local correlations sometimes observed between minds, and the way that conscious experience seems to transcend the boundaries of individual neural networks. The physicist David Bohm proposed that consciousness and matter might both be manifestations of a deeper, implicate order, an underlying field of information and meaning from which both physical reality and conscious experience emerge. While Bohm's ideas remain controversial and unproven, they point toward the possibility that the separation between mind and matter might be less fundamental than our everyday experience suggests. As you sit quietly and notice the quality of your own awareness, you might sense something field-like about consciousness itself. Your awareness doesn't seem to be located in any particular place within your body. It's more like an open space within which all experiences arise and pass away. This space of awareness has a naturally expansive quality that doesn't seem bounded by the physical limits of your brain or body. This field-like quality of awareness is most apparent in states of meditation or deep contemplation, when the usual contents of consciousness become quiet and the space of awareness itself becomes more prominent. In these states, many people report a sense of boundless awareness that seems to extend beyond the individual self, connecting with something vast and fundamental. While these experiences don't constitute scientific evidence for a field theory of consciousness, they point towards something important about the nature of awareness that our materialist assumptions might overlook. Whether consciousness literally has field-like properties, or whether these experiences reflect something else entirely, they remind us that consciousness has qualities that are difficult to explain through conventional neuroscientific approaches alone. As we've journeyed through these parallels between quantum mechanics and consciousness, you might be wondering how these insights apply to everyday experience. The quantum world seems so removed from daily life that it's easy to dismiss these ideas as abstract philosophical speculation. But the principles we've been exploring, the participatory nature of observation, The role of attention in shaping experience, the interconnected quality of consciousness, show up in countless ways in ordinary life. Consider how your expectations influence what you perceive and experience. When you approach a social situation expecting conflict, you're more likely to notice signs of tension while overlooking gestures of goodwill. When you expect beauty in your environment, you become more sensitive to aesthetic qualities that were always present but previously unnoticed. Your expectations don't create reality, but they participate in determining which aspects of reality become vivid in your experience. This observer effect extends to your relationship with your own inner life as well. When you approach your emotions with curiosity and acceptance, they often reveal depths and nuances that weren't apparent when you met them with judgment or resistance. When you observe your thoughts with gentle awareness, you might discover that many of them are less solid and persistent than they seemed when left unexamined. The practice of mindfulness meditation involves learning to observe the contents of consciousness without immediately trying to change them. But practitioners quickly discover that the very act of mindful observation inevitably influences what's being observed. Thoughts that seemed overwhelming when resisted often dissolve when met with accepting awareness. Emotions that felt stuck when avoided sometimes flow and transform when welcomed with gentle attention. This doesn't mean that mindfulness practice is a form of quantum mechanics. The mechanisms involved are psychological rather than quantum mechanical, but the parallel is illuminating. In both quantum measurement and mindful observation, the act of looking participates in determining how possibilities unfold into actualized experience. Take a moment to notice this in your own experience right now. As you've been listening to these ideas, your understanding has been emerging through the interaction between your attention and the concepts being presented. You're not just passively receiving information, but actively participating in how these meanings crystallize in your awareness. Some ideas resonate deeply, while others remain peripheral. Some connections emerge spontaneously, while others require more conscious effort to understand. This participatory quality of learning and understanding reflects something fundamental about how consciousness engages with reality. You're always in relationship with what you're observing, whether it's external phenomena or the contents of your own mind. This relationship is creative and dynamic rather than passive and static. While we must be careful not to overstate the scientific connections between quantum entanglement and human relationships, there's something profound to be explored metaphorically about the non-local connectivity that seems to characterize deep human bonds. When you're closely connected to someone, whether through friendship, love, or shared purpose, there's often a sense of instantaneous emotional resonance that transcends physical proximity. Parents frequently report sensing when their children are in distress, even when separated by great distances. Long-term partners often find themselves thinking about each other at the same moments, or arriving at similar insights without explicit communication. Close friends sometimes call each other at precisely the moment when contact was most needed. While these experiences likely involve subtle psychological and social mechanisms rather than literal quantum entanglement, they point towards something important about the naturally interconnected quality of conscious beings. The boundaries we draw around individual minds and hearts are more permeable than our everyday assumptions suggest. Through empathy, you can participate directly in another person's emotional state. Through conversation, you can share not just information, but something of your inner world itself. Through creative collaboration, separate minds can give rise to insights that neither could have generated alone. These forms of connection don't require quantum entanglement to be profound and meaningful. They reflect the fundamentally relational nature of consciousness and the way that individual awareness naturally opens toward and includes other conscious beings. The love you feel for others isn't contained within the boundaries of your individual self. It's a field of connection that transcends those boundaries while remaining grounded in embodied individual experience. As you reflect on the important relationships in your own life, you might notice how these connections have shaped who you are in ways that go beyond simple influence or learning. The people you're closest to become part of your inner world, contributing to the ongoing dialogue of consciousness that shapes how you see yourself in reality. This isn't quantum entanglement in the literal sense, but it reveals something about the naturally interconnected quality of conscious experience. This interconnected quality becomes particularly apparent in moments of shared meaning or mutual understanding. When you're in deep conversation with someone and suddenly find yourselves exploring ideas that neither of you could have reached alone, there's a sense of participating in something larger than individual consciousness. These moments of creative collaboration point toward what philosopher Martin Buber called the between, a space of shared meaning that emerges from but transcends individual perspectives. One of the most profound implications of both quantum mechanics and contemplative investigation is how they challenge our assumptions about separation and independence. In the quantum realm, entangled particles share properties in ways that transcend spatial separation. In consciousness, the boundaries between observer and observed, between self and other, between inner and outer experience, often prove to be more fluid and contextual than our everyday experience suggests. This doesn't mean that individual identity is an illusion or that separation doesn't exist at certain levels of description. Rather, it suggests that separation and connection are both valid and important aspects of reality, neither more fundamental than the other. The challenge is learning to hold both perspectives simultaneously, honoring the reality of individual experience while recognizing the deeper interconnection that underlies apparent separation. Many contemplative traditions have pointed toward this recognition through different language and frameworks. The Buddhist concept of interdependence suggests that all phenomena arise in relationship rather than existing independently. The Hindu concept of non-duality points toward an underlying unity that includes but transcends apparent diversity. The Christian mystical tradition speaks of a love that. Indigenous wisdom traditions often emphasize the interconnected web of relationships that connect all beings and phenomena. While these traditional insights don't constitute scientific theories, they point towards something that quantum mechanics has revealed through rigorous mathematical investigation. Reality, at its deepest level, appears to be more interconnected and relational than our classical assumptions suggested. The hard boundaries between separate objects, between observer and observed, between mind and matter, may be conventional rather than fundamental. As you explore this possibility in your own experience, you might notice how the sense of being a separate self, observing an external world, begins to soften around the edges. When you're deeply absorbed in a beautiful sunset, where exactly is the boundary between the perceiver and the perceived? When you're listening to music that moves you deeply, is the beauty in the music itself, in your consciousness, or in the relationship between them? These questions don't have simple answers, and that's precisely the point. The either-or logic that dominates everyday thinking, either the beauty is in the object or it's in the subject, either particles are separate or they're connected, gives way to a more nuanced Bothan perspective that can hold paradox and complexity without needing to resolve everything into simple categories. Take a gentle breath here and notice how even this simple act involves a kind of collapse of separation. The air you're breathing was just part of the environment around you, and now it's becoming part of your body, carrying oxygen to your cells and removing waste products. The boundary between inner and outer is constantly being dissolved and reformed with each breath, a reminder that the apparent separation between self and world is more fluid than it initially appears. One of the most beautiful parallels between quantum mechanics and consciousness emerges when we consider creativity and the birth of new ideas. In the quantum realm, genuine novelty emerges from the measurement process. New information comes into existence that wasn't present before the measurement occurred. Similarly, in consciousness, genuine insights and creative breakthroughs often emerge from states of not knowing, bringing something genuinely new into awareness. Consider how creative insights typically arise in your own experience. You might be working on a problem or exploring a question for days or weeks without making progress. Then, often when you're not actively thinking about it, perhaps while walking, showering, or falling asleep, a solution suddenly emerges fully formed in consciousness. Where did this insight come from? It's as if the mind had been exploring multiple possibilities in the background before one solution crystallized into clear awareness. This process resembles what physicists call spontaneous symmetry breaking in quantum field theory, where a system in a symmetric state spontaneously transitions to a less symmetric state, giving rise to new properties and phenomena. The creative process often involves a similar dynamic, a period of open exploration where multiple possibilities exist in potential, followed by a moment of crystallization where one possibility emerges clearly. The mathematician Henri Poincaré described this process beautifully in his analysis of mathematical discovery. After intensive conscious work on a problem, he would often set it aside and engage in other activities. Then, at unexpected moments, while boarding a bus or walking on a beach, complete solutions would suddenly appear in consciousness, as if they had been working themselves out in the unconscious background. This creative process suggests something profound about the relationship between consciousness and the unknown. Rather than creativity being simply a recombination of existing knowledge, it often involves a kind of communion with possibilities that weren't previously accessible to awareness. The creative person serves as a kind of detector or antenna, allowing new patterns and insights to emerge from the field of potential knowledge. Some artists and writers describe feeling like conduits or channels for something larger than their individual creativity. They report experiences of receiving ideas, melodies, or images that seem to come from beyond their personal knowledge and intentions. While these experiences don't require supernatural explanations, they point towards something important about how consciousness relates to the creative dimensions of reality. As you reflect on moments of insight or creativity in your own life, you might notice how they often involve a quality of receptivity rather than forcing. Like quantum measurements that allow possibilities to collapse into definite outcomes, creative insights seem to require a kind of open attention that allows new patterns to emerge from the background of awareness. One of the most fascinating parallels between quantum mechanics and human experience concerns what philosophers call the problem of personal identity. Just as quantum systems exist in superpositions of multiple states until measured, you might notice that your sense of self exists in a kind of superposition of multiple possible identities until circumstances call forth particular aspects of who you are. Consider how different social contexts seem to activate different versions of yourself. The person you are with your family might be quite different from who you are at work, which might be different again from who you are when alone in nature. Each context seems to collapse the superposition of possible selves into a particular identity, much like how quantum measurements collapse superpositions into definite outcomes. This doesn't mean that you don't have a core identity or that the self is completely arbitrary. Rather, it suggests that identity might be more contextual and relational than we typically assume. Just as quantum properties emerge from the interaction between systems and measuring devices, personal identity might emerge from the interaction between your consciousness and the various contexts and relationships you find yourself within. The meditation teacher and philosopher Sam Harris has pointed out that when you look carefully for the self that seems to be having experiences, it's remarkably difficult to find. There are thoughts, sensations, perceptions, and emotions, but the thinker, feeler, and perceiver often seems absent when sought directly. This isn't because the self is an illusion, but because it might be more process-like than thing-like, more relational than independent. This process view of identity aligns with certain interpretations of quantum mechanics that suggest particles aren't really separate entities, but rather patterns of activity in underlying fields. Similarly, personal identity might be better understood as a pattern of consciousness rather than a fixed entity, a dynamic process of experiencing rather than an experiencer who has experiences. As you explore this possibility, you might notice how your sense of self changes depending on what you're paying attention to. When you're absorbed in a challenging task, the sense of being a separate self often recedes into the background, and there's simply the activity itself. When you're in deep conversation with someone you care about, the boundaries between self and other often become fluid and permeable. These shifts in the sense of identity aren't problems to be solved, but natural features of how consciousness operates. Like quantum systems that can exist in different states depending on how they're measured, consciousness can organize itself around different centers of identity depending on the context and quality of attention present. Recent developments in theoretical physics have suggested that reality might have a holographic structure, that all the information in a volume of space can be encoded on its boundary, like a hologram where the whole image is contained in each part. This holographic principle has profound implications for how we understand the relationship between parts and wholes, and it offers fascinating parallels to how memory and consciousness seem to operate. Consider how memory works in your own experience. A single sensory cue, a particular scent, a fragment of music, or a glimpse of light can suddenly bring back an entire complex of memories, emotions, and associations. It's as if the whole of a past experience is somehow encoded in each of its parts, allowing any fragment to reconstruct the totality. This holographic quality of memory extends beyond individual recall to include the way that consciousness seems to contain multiple levels of experience simultaneously. Right now, as you listen to these words, you're simultaneously aware of the meanings being conveyed, the sound or internal voice speaking them, the physical sensations in your body, the emotional qualities present in your awareness, and the broader context of your life situation. Each aspect contains information about the whole of your current experience. Some researchers have suggested that the brain itself might operate according to holographic principles. The neuroscientist Carl Pribram proposed that memories might be stored throughout the brain in a distributed, holographic fashion rather than being localized in specific neural circuits. While this remains speculative, it offers an intriguing framework for understanding how consciousness integrates information across different neural networks. The holographic metaphor also illuminates something important about how individual consciousness relates to collective or universal consciousness. Many contemplative traditions suggest that individual awareness is like a wave on the ocean of cosmic consciousness, distinct but not separate, containing the information of the whole while maintaining its particular form and perspective. This doesn't mean that individual consciousness is identical to universal consciousness, any more than a wave is identical to the ocean. Rather, it suggests a nested relationship where each level of organization contains information about and participates in larger wholes. Your individual awareness contributes to and draws from collective human consciousness, which participates in the broader field of consciousness that some traditions associate with the cosmos itself. As you contemplate this possibility, you might notice how your awareness naturally opens toward increasingly larger contexts of meaning and connection. The concerns that preoccupy individual consciousness, personal desires, fears and ambitions, don't disappear, but they begin to be held within broader perspectives that include but transcend purely personal considerations. Throughout this exploration, we've been investigating parallels between quantum mechanics and consciousness that remain largely metaphorical rather than literal. While these parallels don't constitute scientific proof of quantum theories of consciousness, they point towards something profound about the nature of reality that both physics and contemplative investigation seem to be discovering from different angles. Both quantum mechanics and careful introspection reveal that reality is far more participatory, relational, and mysterious than our everyday assumptions suggest. Both challenge the sharp boundaries between observer and observed, between subjective experience and objective reality. Both point toward a universe that's constantly creating itself through interactions rather than simply unfolding according to predetermined patterns. Yet, perhaps most importantly, both quantum mechanics and consciousness studies invite us into a more humble and wondering relationship with existence itself. The deeper we investigate reality, whether through scientific instruments or contemplative inquiry, the more mysterious it becomes. This isn't because our tools are inadequate or our understanding is limited, though both are certainly true. Rather, it seems to be because reality itself has an inexhaustible depth that always exceeds our attempts to capture it completely. As we reach the end of this exploration into the mysterious dance between quantum mechanics and consciousness, take a moment to appreciate the profound shift in perspective we've experienced together. We began with the startling recognition that quantum calculations are occurring in every cell of your body right now, and we've journeyed through territories where the boundaries between mind and matter, between observer and observed, become beautifully blurred. What we've discovered isn't a new theory of everything or a scientific proof that consciousness creates reality. Rather, we found something perhaps more valuable, a recognition that the universe is far more participatory, mysterious, and interconnected than our everyday experience suggests. Both quantum mechanics and careful investigation of consciousness point toward a reality that's constantly creating itself through relationships and interactions rather than simply unfolding according to predetermined patterns. The parallels we've explored between quantum measurement and conscious attention, between superposition and the multiple possibilities that hover in awareness between entanglement and the deep connections we feel with others remain largely metaphorical rather than literal. But these metaphors illuminate something profound about the nature of existence that both rigorous science and contemplative wisdom seem to be discovering from different angles. Perhaps the most important insight emerging from this exploration is an invitation to humility and wonder. The deeper we investigate reality, whether through sophisticated scientific instruments or through the refined awareness of contemplative practice, the more mysterious it becomes. This isn't a failure of understanding, but a recognition that reality itself has an inexhaustible depth that always exceeds our attempts to capture it completely. As you return to your daily life, carrying these insights with you, you might notice subtle shifts in how you relate to uncertainty, to the boundaries between self and world, to the participatory nature of your own awareness. The solid world of separate objects doesn't disappear, but it begins to reveal itself as emerging from something far more fluid and interconnected than classical physics ever imagined. The quantum realm and the realm of consciousness both remind us that we're not separate observers of an external reality, but intimate participants in an ongoing creative process that we're only beginning to understand. Your awareness, your questions, your wonder itself participates in the endless conversation between mind and cosmos that gives rise to everything we call real. Rest here for a moment in the mystery we've explored together. You don't need to understand every implication or resolve every paradox. Like the quantum world itself, the deepest truths often resist being captured in final explanations, preferring to remain alive in the space of ongoing discovery and wonder.